Good day, everyone. The topic for today's discussion is Routh Hurwitz Stability Criterion. I am S. Maria Anthony, working as Assistant Professor in the Department of ECE at KIT Kalinger Karnataka Institute of Technology, Coimbatore. Routh Hurwitz Criterion is basically a technique to determine the stability of a control system. It states that any system can be stable if and only if all the roots in the first column of the Routh table has the same sign. If the roots of the first column does not have the same sign, that system is said to be an unstable one. The number of sign changes in the first column, what we'll get from the Routh array, will indicate the number of roots that will be present in the right half of S plane. For determining the stability of a system, we need to find the roots of the characteristic equation for a given system. The characteristic equation can be obtained by setting the denominator of a closed loop transfer function to 0. Basically, these characteristic equations are large and complex. Hence, they are difficult to simplify them into roots whenever these equations are of order 4 and above. For such situations, what we'll do is we have this Routh Hurwitz stability criterion that provides an easy and quick method to determine the stability. We need not split the characteristic equation to obtain the roots. We can straight away take that characteristic equation and determine the roots. Necessary condition for Routh Hurwitz stability. The necessary condition for Routh Hurwitz criteria is that the coefficients of the characteristic equation should be positive one. There shouldn't be any negative values, and also the characteristic equation should not have any zero valued coefficient. All the powers in the characteristic equation must be a non-zero value. This is a representation of a characteristic equation for an order n. So we will have the equation in this fashion: a naught s power n plus a1 s power n minus 1, a2 s power n minus 2, so on, a of n minus 1 s power 1, a of n s power 0 equal to 0. So this is how an characteristic equation will be represented. Here n represents the order of the characteristic equation. Sufficient condition for Routh Hurwitz stability. Sufficient condition for Routh Hurwitz stability is that all the elements of the first column in the Routh array should have the same sign. It could be either positive or a negative. Now let us consider the procedure for creating the Routh array. First, the two rows of the Routh array can be obtained or it can be filled from the coefficients of the characteristic equation. We'll start with the coefficient of s power n and we'll continue up to the coefficient of s power 0. The remaining two rows of the Routh array, they will be filled by using a mathematical calculation which will be mentioned below, and this process of calculation to find the elements of the rows will be continued till we get the column element of row s power 0. If any row elements that is framed in the row table has the same common factor, then we can divide the row elements for simplification. So this is an example for Routh array or Routh table, general representation of this Routh table. So if we have the characteristic equation in this fashion, that is a naught s power n plus a1 s power n minus 1 plus a2 s power n minus 2, so on till a of n minus 1 s1 and a of n s naught, we can form this Routh array by taking the elements or the coefficients from the characteristic equation and fill the first two rows, these two rows, s power n and s power n minus 1, right? So there is a particular order by which these elements are getting filled up. So first what we'll do is we'll take a naught and we'll fill the first element, right? Then we will be taking the not the next element, the very next element, right? For example, if I take the first element s power n, I'll be taking the coefficient of s power n minus 2 and fill the second element in the first row. Then similarly, the next element will not be taken. I'll be taking s of n minus 4's coefficient, which is going to be a4, right? So you can see here this is in sequential order, that is a naught, a1, a2, a3, so on. But when we fill the first row, when we take a naught, the next element in the first row will be a2, the next element will be a4, then next will be a6. Similarly, the second row will be taking the odd numbered coefficients. We'll be having a1, a3, a5, A7 and so on, right? Then from these two rows, what we can do here is we can form the next row, that is s power n minus 2. So if you want s power n minus 2, the mathematical calculation what we'll use here is we'll multiply a1 into a2. So you can see here a1 into a2. Then there is a subtraction here minus a3 into a0. So you can see here a3 into a0. So this factor is getting divided by a1, this base element a1. So this is how we'll be able to get this particular element, that is your first element of your row s power n minus 2. So if I want the next element b2, so again a1 will be the base element here. A1 will now be multiplied with a4, right? So this second column will not be considered for multiplication. We'll consider the third column here, right? A1 into a4. Again there is a subtraction here minus a5 into a0 divided by again the base element a1, right? So using this we'll be able to get the third row elements. But when we move on to the fourth row, what we'll do is we'll consider the first row and second row for the mathematical calculation to obtain the elements of fourth row. We'll not be considering the first row, right? So if at all we want the fourth row elements, we'll be doing that calculation using the row second one and the third row. So if you want the element C1, we'll multiply A3 into B1 minus A1 into B2 divided by B1, right? So here the base element is going to be B1 here. So B1 into A3 minus A1 B2 divided by B1. Right? Then similarly C2, if I want, again this is going to be the base element B1, B1 into A5 minus A1 into B3 divided by B1, right? So the same procedure will be repeated till we get the elements of s power naught. Let us consider an example for the Routh Hurwitz stability criterion. Here the characteristic equation given is s power 4 3s power cube. Yes, so this is the characteristic equation given, s power 4 3s power cube 3s square plus 2s plus 1 equal to 0. So the first step in identifying this stability of this particular characteristic equation is we'll verify the necessary condition for Routh Hurwitz stability criterion. So first necessary condition is all the coefficients of the characteristic equation must be non-zero and it must be positive also. So you can see here s4 s3 s2 s1 and this is s power 0. All the powers of this particular characteristic equation are non-zero values and they are also positive also, there is no negative sign in between. So it satisfies the first necessary condition. Then step 2 is we have to frame the Routh table or Routh array. So Routh array can be formed from the characteristic equation coefficients. So s power 4 has a coefficient of 1. We'll substitute in the first row first element. Then the second element of first row will be taken from the alternate powers. So if the highest power is even, we'll take the even values to fill the first row. If at all the highest value of the characteristic equation is the odd value, we'll fill the first row with odd valued power coefficients. So since the characteristic equation here has a even value, that is s power 4, we'll use s power 4's coefficient 1 here to fill the first element. Second element is going to be 3s square, right? S square's coefficient is 3, we'll put 3 here. Then the alternate value is going to be s power 0 whose coefficient is 1. Hence we have completed the first row of the Routh table. Coming to the next row of the Routh table, which has the coefficient s power 3. So here coefficient of s power 3 is going to be 3 here. So first element of second row is going to be 3. Then the next element of the second row is going to be s power 1's coefficient, that is 2. So we'll put 2 here, right? So there is no element over here, so this is supposed to be 0 here. Now coming to the third row of the characteristic or the Routh table here, what we'll do is we'll do a small mathematical calculation here. The mathematical calculation will be done in such a way that 3 is multiplied by 3 and that is to be subtracted by the product between 2 into 1. So you can see here this calculation is done over here, 3 into 3 minus 2 into 1 divided by 3, right? So this element is going to be base for this particular calculation, by which we'll be dividing all the elements here. So you can see here it is divided by 3. So the final value is going to be 9 minus 2 by 3 is going to give us 7 by 3. For the next element, again we'll consider this to be the base here. We'll multiply 3 into this element 1, then minus 1 into 0 here, right? So if we simplify this, we'll get 3 by 3 is going to be 1 here, right? Then the next row, what we'll do is we'll do the same multiplication, I mean the mathematical calculation, but the thing is we'll take the adjacent two rows, right? If power is s power 1, we'll consider the rows of s power 2 and s power 3. Now the multiplication calculation will be like this, that is we'll do this 7 by 3 into 2 minus 1 into 3 divided by this element value is 7 by 3, right? So if we simplify this, we'll be getting 5 by 7, right? So if I try to multiply with the next element here, you can see both these values are going to be 0 here. So we will not be having element over here, right? So this is supposed to be 0 here. Then moving on to s power 0 row. So again here we'll do this mathematical calculation by multiplying 5 by 7 into 1 minus 7 by 3 into 0, right? So if we divide this, we'll be getting 5 by 7 into 1 divided by 5 by 7, right? So what will happen is ultimately this will give us 1, because 5 by 7 by 5 by 7 is equal to 1 here, right? So you can see here this is the first column for our consideration to determine the stability of your characteristic equation or the control system here, right? So we'll consider the elements of the first column here, right? So we'll have 1 here, 3 here, plus 7 by 3 plus 5 by 7 plus 1, right? So you can see here all these values are positive values, there are no negative values here. So that will be our step 3, right? Step 3 is we'll verify the first column elements here, right? So since all the elements are positive here and there is no sign change in the first column of the Routh array, we can say the given characteristic equation or the given control system corresponding to that particular characteristic equation is a stable one. Now there are a few advantages of Routh Hurwitz stability. The advantages are it takes less calculation time. The number of roots in the right half of the S-plane can be found in case of an unstable system. Range of K for the system to be stable can be calculated. Similarly, frequency of oscillation at the steady state can also be calculated. Disadvantages of Routh Hurwitz stability is it is valid only for real coefficient of characteristic equation. It is unable to give exact locations of the closed loop poles, and it doesn't suggest any methods for stabilizing a unstable system, right? So it is just used for determining whether the system is an unstable one or an unstable one, and it is also applicable only to a linear system. It is not applicable to a non-linear system. Thank you for your patient listening.